Good morning, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we're going to continue conservation of energy, but we'll look at practice problems that involve air resistance, internal energy, and work. So let's look at the first one. A 2-kilogram ball suspended 100 meters above Earth falls towards the ground. Fortunately, air resistance is present, causing the 50 joules of energy of the hail to be converted to heat through internal energy. How fast is a hail falling an instant before it hits the ground? So if there weren't air resistance or internal energy, the hail would be falling pretty fast, and it might even hurt you pretty bad. So let's look at LOL diagrams before and after to help analyze this problem and solve for the final velocity of the hail. So we've got our before, after, and this time in the O we have air resistance or internal energy, so yes, this can be converted to a different form. So before, our options are potential, kinetic, work, and internal energy, and same for after. Potential, kinetic, work, internal energy. Okay, so based on the problem, what type of energy does the hail have before? Well, it only has potential energy. No kinetic, no work, no internal. After, what type of energy does it have right before it hits the ground? Well, it's right before the ground, so no potential. It's got kinetic because it's moving. No work is being done on it. And some of it was converted into internal. So we've got kinetic and internal energy. So based on our LOL, we could write our formulas. We have PE before is equal to KE after plus Q. So based on our formulas of potential and kinetic, we can now expand these. Potential is mgh, we'll put before. It's equal to 1/2 mv squared, we can put after, plus q. And our goal is to solve for the velocity after, or velocity right before it hits the ground. So we'll first subtract our q, mgh before minus q, multiply everything by 2 to get rid of the 1/2, divide everything by the mass, and square root it to get the v by itself. Now all we do is just plug and chug. V after is the square root 2 times 2 kilograms times 9.81 meters per second squared times 100 meters, extend our square root, minus 50 joules of internal energy all over the mass, again 2 kilograms. And we get a velocity of the ball after, or the hail, sorry, to be 43.7 meters per second, which is still pretty darn fast if you ask me. Alrighty, this time we're going to solve a problem that involves work and kinetic energy, or in the work-kinetic energy theorem. So why don't you read the problem and try and label your LOL diagrams while reading it. In the meantime, my cat decided to learn some physics, and he's sitting right above my shoulder. Say hi to Leo. Hopefully he doesn't get in the way. Okay, so we have a 35-kilogram car traveling at a constant speed of 25 meters per second. Well, that means it has kinetic energy because it's moving. No potential. What is the total work that must be done to increase its speed to 30 meters per second? So we also have to do work to it, no internal, to increase its speed. So the work is before. After, no potential. It's increased its speed, so it's increased kinetic energy. No work, no internal. So we've got KE before plus work before is equal to KE after. and we want to find the work being done. So why don't we just subtract the KE now? So we have work before is equal to kinetic energy after minus kinetic energy before. And now we'll just break down each formula. Work before is 1/2 mv after squared minus, sorry about that, minus 1/2 mv before squared. And then we just plug and chug. So work before is 1/2, 35 kilograms. That's a very light car. I'm not sure where that number came from. Times, I think it was going at 30 meters per second after, quantity squared, minus 1/2 again, 35 kilograms, times before 25 meters per second squared. And again, that's quantity squared. Plug and chug. Work before is equal to 8,938 joules. And that's our last video on conservation of energy. Hope you found this one useful. See you next time.